Okay, welcome to this video on acid-base equilibrium. This is the second part of our series, and I've already gone through this problem. If you want to check that out, that's the first video. But moving on, let's work on the example below. So, like I said in the first video, acids will have a positive formal charge or a neutral formal charge, and bases will have a negative formal charge or a neutral formal charge. Well, in this case, both molecules are neutral, and we're left thinking, well, which ones are acid and which ones are base? Well, we should know that this molecule right here is sulfuric acid, and sulfuric acid by name should indicate that this molecule is an acid. Sometimes it's not that easy, but I will go through some problems in our series on deciding which molecule is more acidic and which one will be our acid and which one will be our base. So this just happened to be sulfuric acid, and we should be able to identify that by its structure. So this would obviously be our base. Let's draw in our lone pair on our base, because the lone pair will be interacting with a proton to form a bond. And once again, we're lucky because this molecule only has a lone pair on this oxygen, because sometimes we'll have more lone pairs on atoms in a molecule and we'll be left thinking which atom in the molecule is more basic, which will gain that proton. And that will also be in a video I'll be making, because problems can get pretty hard pretty quick. So what do acids do? Acids give off protons. They donate protons, while the base will accept the proton. And we show that by using electron arrows to resemble forming bonds and breaking bonds. And in acid-base problems, we always start at the base. So we'll draw an arrow right here onto our hydrogen atom, or hydrogen ion, because we're just taking the proton. And we'll show that we're breaking that bond and putting a lone pair on this oxygen. So let's see here. Let me copy this molecule to the right hand side so we save some time. Okay. And let me take this molecule. Whoops, that's not good. There we go. Oh my goodness. There we go. Okay, let me just put a plus between these just to show. Okay, so what did we do here? We formed a bond on this oxygen atom by using this lone pair of electrons. So we formed a bond. Let me delete this lone pair because we formed a bond with a hydrogen ion or a proton. Let me just duplicate this. Take this hydrogen. All right, there we go. So what do we do here? We made this, to use this lone pair on this oxygen to take a proton off of this molecule and broke a bond and put those, which will be a lone pair, broke this bond, had electrons between them, and put them onto this oxygen. So let's draw in our lone pair of electrons. Let me also, so this doesn't get confusing, we took that proton, put it onto this molecule, and we broke this bond and put those electrons onto this oxygen atom. And since this oxygen atom was neutral with that bond, with that hydrogen, we should know that electrons are negatively charged, so this oxygen will also have a negative formal charge. You can check the formal charge using that long formula, but as we start doing problems and you have less time, you should just know that when we're moving electrons, that's a negative charge. But also, I cannot forget here, this oxygen has a positive charge. And why is that? It was neutral over here, and it gained a proton, which is positively charged. If you check the formal charge formula, this indeed has a positive charge on the oxygen. So the next step is to identify our conjugate acid and our conjugate base. Our conjugate acid, which I'll represent by Ca, will be the molecule that gained a proton. And the molecule that gained a proton is this molecule right here. So here's our conjugate acid. And our conjugate base is the molecule that lost a proton. that'd be sulfuric acid. So this molecule right here is the conjugate base of sulfuric acid. Now, how do we determine which side is favored? Well, we compare our conjugate base to this right here, our conjugate base to our base. Now, this side, let me draw a big arrow, is favored. Now, why? Well, we can see that the conjugate base of sulfuric acid can take a lone pair of electrons on this oxygen and form a double bond right here. And let me just draw that. So we could form a double bond right here. And let me delete that. So we took that lone pair, made a double bond, and then we could take that's getting messy. We could take this bond. It's not going to let me do it because it's an image. So I can't do that. So we'll take this bond right here and we could break it and put a lone pair up here. So what am I trying to say? Well, what I'm trying to say is that this molecule right here can undergo resonance. Let me draw that out. So resonance. And the reason why resonance is so much better is because we can delocalize electrons. And what does that mean? We can move that negative charge and place it on this oxygen and this oxygen by partial charges. So what we're doing is just spreading out our negative charge around this molecule, which will indeed stabilize it. So this side is much more stable because we can make resonance structures with the conjugate base of sulfuric acid. I hope it didn't get too confusing, but if it did, comment down below and I'll help clarify things. And if this video helped you, please give it a thumbs up, subscribe for more videos, and yeah, I hope you ace your exam.